Hello everyone. In this lecture we're going to be talking about orders of the reactions, and the reactions could be zero order, first order, second order, and even third order and more, but it gets complicated as the order of the reactions goes up. So for the most part we focus on the zero order, first order, and second order, but you could be asked the basic questions on the third order and even higher order reactions. Now what does that really mean? Suppose I have a generic reaction where I got A plus B plus C, and then it's going on to make some product. Now, the reaction rate is going to be dependent on the concentration of A, the concentration of B, and the concentration of C. So I can go ahead and write down the rate is going to be some rate constant K, and then I have the concentration of A to the power X, and then I got concentration of B to the power Y, and then I got a concentration of C to the power Z. Now, this X, Y, Z could be any numbers. It could be positives, even fractions, and even negatives as well. But for the most part, you see those positive integers. And if I suppose if I have 1 for x, that means the rate is linearly dependent on the concentration of A, which means if the concentration of A goes up by a factor of 2, then the rate will also increase by a factor of 2. So that's what these orders of the reactions are going to be. So how do you know what x going to be, what y going to be, and what z going to be? That has to be determined experimentally. This cannot be coming from these coefficients. So I know the coefficient right now is 1 in front of each of those reactants, but I cannot use 1 for the orders of these reactions. So when you look at the overall order of this reaction, it's going to be x plus y plus z. And then you can also say x is going to be the order with respect to A, y is going to be the order with respect to B, and z is going to be the order with respect to C. And the overall order of the reaction is just going to be sum of all three of those orders. Like I said, it has to be determined experimentally, and now you could have an overall first order reaction, second order reaction, and a zero order reaction. So let's just talk about those one by one. So suppose I have a first order reaction, so I'm just going to go and write in a genetic reaction where A goes on to make product. If I want to write down a simple rate law expression for this particular order of the reaction, it's going to be rate is going to be equal to some rate constant K, and then the concentration of A to the power 1. So I don't necessarily have to write down 1 here. When you don't write down anything here, that means it's going to be 1. So don't write down anything there. So now this is in a first order reaction with respect to A, and that also makes this overall in a first order reaction. So you want to be able to identify how the equation is going to look like, or the rate law expression is going to look like for a first order, second order, and a zero order reaction. In addition to that, you also want to be able to figure out what's going to be the units for K. When you're trying to figure out the units for K, there is going to be a simple formula that you can always use. I will go ahead and write that down. It's going to be the molarity 1 minus n second inverse, where n is going to be your order of the reaction. So if in this particular case your order of the reaction is first order reaction, then I'll go ahead and plug it in 1 minus 1 second inverse. So 1 minus 1 is going to be 0. So the units for this particular order of the reaction for the first order rate constant is going to be second inverse. So make sure you're able to calculate that. Sometimes you may not have enough information about the order of the reaction, but based on the units, sometimes you can figure out which particular order we're talking about. Okay, so then I do want to mention that remember your molarity. If I go and write that on the side here, molarity is going to be moles over liters. Sometimes you may see that molarity kind of being broken up into further those units. So keep that in mind. In addition to that, what's going to be the units for rate? The rate is going to be your molarity per second, and that's what we talked about in the previous session. The rate is going to be how much the concentrations are changing with respect to the time. So it's going to be the molarity over a second. And again, this molarity could be further broken down into moles over liters, depending on what particular unit you really want to write down for the rate constant K. What's more important is going to be your integrated rate law. So I'm not really going to write down how you drive that, but rather I'm just going to go ahead and write down what it looks like because that's what's going to be more important. So the integrated rate law, it looks like natural log of A at a particular time, concentration of A at a particular time t is going to be equal to negative kt plus natural log of A at 0 time. So your AT is going to be at any given time, whereas your A0 is going to be the initial concentration of A, or the reactant in this particular case. And if I kind of relate this equation to a slope line equation, that's going to be y equals to mx plus b. What that means, this y is going to be the natural log of a t here. Your slope m is going to be given by the negative k here, and then your y-intercept is can be used to calculate the initial concentration or the natural log of a0 there. So another way of saying it's not that easy to find out the initial concentrations of the reactants sometimes, because as soon as you mix those, um, they start reacting with one another and you have products being made. So you can use this equation to figure out the initial concentration of the reactants. Now if I want to plot this, when I'm plotting this, I'm going to have natural log of AT, or concentration, on the y-axis, and your x-axis is always going to be time. So it's going to be extremely important to understand when you're dealing with first order, second order, or zero order reactions, which particular variables you plot and how do your plot looks like. Now when you're looking at this first order reaction, we're plotting the natural log of the concentration versus time, and your plot is going to have a straight line but with a negative slope. So slope in this particular case can be used to figure out the rate constant K. So that's another way of figuring out what's going to be the value for the rate constant. And remember, your slope is a negative here, and that's completely okay because we already have a negative in this equation. So when you do go ahead and get the negative slope and set that equal to the negative k here, so this is actually going to be negative k rather. So when you set that equal to negative k, your rate constant overall comes out to be positive. So make sure you know what to plot when you're looking at the first order reactions. In addition to that, you also want to be able to figure out what's going to be the equation for the half-life. Now, to figure out the half-life equation, and as the definition specify, how long it's going to take before you have half of your original concentration left. So your AT, or the concentration at a particular time t, is actually going to be half of your original concentration. So if I go back and plug this in to my original equation, so we have half of the concentration here, it's going to be equal to negative k, and now instead of writing t, I can go ahead and write down t half and then plus natural log of initial concentration. So I didn't really do anything other than writing half of the concentration instead of natural log of AT. So I'm not really gonna ask you to solve this, and it's unlikely you'll be asked to solve in any class, but be able to kind of manipulate this and at the end of the day know how your equation is going to look like. So at the end of the day, your rate constant, or your t half, is actually going to be equal to natural log of 2 divided by the K. So that's the equation you want to make sure you can memorize. So that's going to be your first order reaction, and instead of natural log 2, you may also see 0.693 over K being written, because remember the natural log of 2 is 0.693. Okay, moving along, let's talk about a second order reaction. So let me make a little bit of space there. So in a second order reaction, you actually gonna have maybe like two reactants very well. You could have two reactants, or maybe you just have one product, one reactant, but it's gonna have a power of two. So I can see a couple of these scenarios there, and I can go ahead and write down the rate law expression for both of those. So I can do rate for this first one, it's going to be the rate constant K, the concentration of A to the power of 2, so that makes it a second order reaction. Or I can go ahead and write down with this next example I have written down. So it's going to be the rate equals rate constant K, A to the power 1 and b to the power 1. So remember, I don't really have to write those ones there. So it's going to be a first order with respect to a and first order with respect to b, and overall it's going to be a second order reaction. So you could see any of those scenarios there. So I'm just going to be focusing on this for the sake of finding the integrated rate law and everything. So the integrated rate law for a second order reaction, and obviously it comes from the basic rate law expression, but like I said, we're not going to be deriving those, but be able to know that equation and use that equation to solve the problems. So the integrated rate law for the second order reaction is going to be 1 over concentration of A at a given time t is going to be equal to kT plus 1 over the concentration of A in the beginning. I can still relate this to a slope line equation, which is going to be y equals mx plus b. So in this particular case, your y-intercept is actually going to be 1 over the initial concentration, and your y-axis is actually going to be 1 over 1 over the concentration of your reactant. So when I'm actually plotting this, how that's going to look like. Okay, let me. So I'm going to have time again on the x-axis, and on the y-axis it's actually going to be 1 over the concentration. So at the end of the day, your equation is going to be actually going to be a straight line with a positive slope. So in this particular case, the slope would be actually equal to the rate constant. And what's going to be the units for rate constant here? So I forgot about that. So let me just go and write that on the top here. So remember, if I'm trying to figure out the units for K, and since this is in a second order reaction, it's going to be molarity 1 minus n. The value of n in this particular case is going to be 2, second inverse. So it's going to be molarity inverse, second inverse being the units for K. If I want to go ahead and break down the molarity, what's that going to look like? Well, remember your molarity is moles over liters. So it's going to be moles over liters, and still it's going to have a -1 there and second inverse. So you want to be able to kind of rewrite that, and when I rewrite it, it's going to be your liter comes to the top because you have a -1 in the power, so it's going to be liters, and moles still going to have a -1, and your second still going to have a -1. So those are going to be the units for the K here. When I'm writing when we're looking at the plot, obviously we're going to have on the y-axis is going to have 1 over the concentration, and your x-axis is always going to stay the same regardless the type of the order of the reaction. It's always going to be the time. Know what variables you're going to be using to plot for the second order reactions. Know your integrated rate law, like this one right there. Simple rate law expression going to look like, be able to figure out or calculate the units there, and half-life finally. So I'm not really going to go ahead and write those values down. So to figure out the half-life, all you really got to do, instead of concentration of A at a particular time t, you're going to be plugging it in A0 or initial concentration over 2, and then figure out the time there. So when I actually do so, and you don't really have to know how to derive it, but rather memorize this formula or be able to use that formula, the T half for a second order reaction, it's going to be equal to 1 over K times the initial concentration. So that's going to be your half-life of the second order reactions. If I look at the difference between the half-life of the first order and the second order reaction, in the half-life of first order reaction, we didn't really have any original concentration or initial concentration. It was only the rate constant that would actually determine the half-life in the first order reactions. But in the second order reactions, the half-life does depend on what initial concentration of the reactant is along with the rate constant. Let's look at the zero order reactions. Now, what that really means? Well, zero order reactions means the concentration of the reactants is not going to be a factor in terms of the rate of that particular reaction. So if I go ahead and write down rate equals some rate constant K times the concentration of A to the power 0. So the concentration of A to the power 0 is just going to be 1. So that means the rate is just going to be equal to the rate constant. And your rate of the reaction is going to be independent of the concentration. If the concentration doesn't change, or even if it changes, your rate is not going to be changing at all. And how would you find the units in this particular case? The units of K, I can go ahead and write down the molarity 1 minus n second inverse, and I know it's in a zero order reaction, so the n value is going to be 0, so it's just going to be molarity times second inverse. So that's going to be your final units, and if I want to go ahead and break down the molarity, it's going to be moles divided by liters second inverse, which I can rearrange it to write down moles times liters inverse times second inverse. So that's going to be your final units for the K in this particular case. As far as the integrated rate law go, it's going to be it's just going to be the concentration of A at a given time. That's going to be equal to negative KT plus initial concentration of your reactant. So make sure you're aware of this equation as well. So a lot of equations in this lecture here. And then when I'm plotting the graph, how's that going to look like? Well, on the y-axis, what we're going to have? We're going to have just going to be just going to be the concentration of A. On the x-axis is still going to be time, and the type of graph we're going to be seeing, it's going to be a straight line with a negative slope again, and the slope here is actually going to be equal to negative k. So you can still find the value of k if you know the slope of these graphs. So suppose you're given a data, and when you're given a data and you're asked to figure out whether it's going to be a first order, second order, or zero order reactions, and sometimes it's not that easy. So what do you really have to do? You're going to have to plot 3 graphs in that particular case. The first graph is going to be natural log of A versus time, and if you do get a straight line with a negative slope in that particular case, then it's going to be indeed a first order reaction. So suppose you did that and did not come out to be a straight line, so then you check for your second order reaction, and the second order reactions will be drawn by doing 1 over the concentration versus time. And if you do get a straight line with a positive slope, then it's going to be a second order reaction. And in case if you don't get it, then you're going to be plotting another graph with the concentration on the y-axis and the time on the x-axis. And in that case, if you do get a slope if you do get a negative slope, then it's going to be a zero order reactions. Okay, so know what you're going to be plotting when you're doing the first order, second order, and zero order reactions. As far as the half-life go for the zero order reaction, it's going to be T half equals concentration of initial concentration divided by 2 times K. So that's going to be your half-life for the zero order reactions. All right, let's try to do this problem here. It says consider this reaction that's written down below and the rate law expression that's written down, and it says how would the rate of the reaction changes if the concentration of A is increased by a factor of 2. So when we say increased by a factor of 2, it's just another way of saying that it's doubled up. And then the concentration of B is tripled and the concentration of C is halved. So you got to figure out what your new rate gonna be in that particular case. So suppose if I go ahead and write down, so this is my original rate law expression. So I'm just gonna copy that down a little bit here. And then my new concentration is going to be your A goes up by a factor of 2, so it's going to be 2A, and then B is tripled, so it's going to be 3B, and then your C is half, so it's going to be C over 2. So I'll go back and plug those values in there now. So it's going to be rate equals K. So your A is doubled, so it's going to be 2A to the power 1, so I don't really have to write down 1 there. And your B is going to be 3B to the power 2, and your C is going to be C over 2 to the power 3. So the easiest way to do this problem is to kind of figure out what those numbers are going to end up at the end of the day and leave the A, B, C as it is. So I'll just take that out. So it's going to be 2 times K concentration of A, and what happens to the 3 that's going to be in front of B? Well, it's being squared, so it's going to be 9, and then you leave the B inside as it is. And then what happens to the C over 2? Well, that's going to be cubed, so your 2 is going to become 8, so it's going to be 1 over 8, because remember, you are also cubing the 2 that's in the denominator along with cubing the C. So and then you leave the C as it is inside the parentheses there. So then all those numbers, what they're going to come out to be, we got 2 times 9 divided by 8, and then the rest of the stuff stays the same as you have seen in the original rate law expression. So when I do this math, it's going to be 9 times 2 divided by 8, so that comes out to be 2.25, and the rest of your stuff stays the same. It's going to be A to the power 1, B to the power 2, and C to the power 3. So what that really means, we have this new reaction rate that's going to increase by a factor of 2.25 anytime you changes the concentration of A, B, and C according to this particular equation here, according to this particular question. And that's how you're going to be doing a lot of these questions. You may not have 3 reactions, you may have only 1, or you may have 2 reactions and stuff like those. Just as a bonus, what's going to be the rate constant unit here? So let me talk about the units of K here. The units of K, since overall it's going to be a 6th order reaction, because you got 3 plus 2 plus 1, so it's a 6th order reaction. So I'll go ahead and write down m1 minus n second inverse. So then it's going to be m1 minus 6 second inverse. So at the end of the day, it's going to be molarity minus 5 second and minus 1 in the power. So that's going to be your final units for the rate constant here. If you have any questions on any of those concepts, feel free to leave any comments in the section below.